Hello Math 1093, this is Dr. P with a video about exam question Q15. Now this is one where some of you had some success, but a bunch of you did basically nothing on this, and I don't know whether that was because you were worried about time for the rest of the exam, so wanted to hand this in earlier, if it's just you had no idea how to graph a function in polar coordinates. But if you don't have any idea, this is the time to learn. So we're going to talk about how to graph this function, r of theta equals 1 minus 4 sine of theta, in polar coordinates. So first of all, a little bit of background. This is very different from graphing in Cartesian coordinates. So when I graph in Cartesian coordinates, I have some function f of x, and then that depends in some way on x. This is just an example. F of x equals x squared. So when I'm graphing a function in Cartesian or rectangular coordinates, I have this independent variable x, which is measured along this axis. And then I have a dependent variable, which I could call y, or I could call f of x, which is measured along this axis. All right, so I'll call that axis the f of x axis, all right, or the y axis. And then what I do is I track changes in x, and then track the corresponding changes in f of x. So I just sort of let x lazily advance along to the right, and then notice that as x increases, y increases faster and faster. And I sort of graph in this direction. I can also graph backwards by letting x be negative. But the main thing to notice here is that as the variable on this axis increases or decreases, the variable on this axis increases or decreases. Now what makes graphing in polar coordinates different is that I'm thinking of theta as the independent variable, which is already a little bit weird because in polar coordinates, the polar coordinates are r comma theta. So my independent variable is in this second position here. This is my independent variable. And then this is my dependent variable. It's usually best to think of it that way anyway. There's no reason why r has to be the dependent and theta the independent. But in this function here, I'm treating theta as the independent variable and then defining r in terms of that. So it makes the most sense to do that. Anyway, so I have my independent variable, which doesn't really run along an axis so much as it runs along possible measures of an angle or positions on a unit circle. Okay, and theta could continue to advance, and I would keep going this way. And as I do that, as theta runs in this direction, counterclockwise or clockwise, my radius or distance from the origin changes. So I'm going to end up tracing out some shape. So for example, suppose that when r is 0, now this is not true of the function I'm going to graph, but suppose that when theta is 0, my r is 5, and then let's say that as theta increases, r increases and then decreases. I'm going to get some shape. Theta is going to advance. My radius or distance from the origin will increase and then gradually decrease back. Okay? And then perhaps at some point r is 0, which means I go through the origin because when r is 0, that's where I am. And then maybe r is negative at some point, and then things keep progressing this way. But anyway, the point is, in a rectangular graph or a graph in rectangular coordinates, I'm sort of running in this direction and then tracking decreases or increases in the dependent variable. Here I'm running in this direction, the counterclockwise direction, and tracking increases or decreases in distance from the origin. So a little bit different. Anyway, probably the first thing that we should do if we have no idea what graph that is, and there's no reason why we have to know, is create a table of values. And this should be the first thing we do anytime we're faced with a graphing task whose answer we don't know just off the top of our heads, is investigate. Create a table of values. And values of theta that tend to be particularly nice for problems like this are multiples of pi over 2. So pi over 2, pi, and 3 pi over 2. Those are good values to start with. I don't think that they're the only ones that we need, but they will help. Alright, so anyway, r of theta is always going to be 1 minus 4 sine of theta. So at this point it's kind of a test to see whether you can quickly calculate values of sine theta. Now you have a unit circle handout on one of the pages of your test, so you should be able to retrieve the correct values. But when theta is 0, 1 minus 4 sine of theta is 1 minus 4 times 0, and that's 1. When theta is pi over 2, I get 1 minus 4 times, let's see, sine of pi over 2 is 1, so I get negative 3. When theta is pi, I get 1 minus 4 times sine of pi, which is 0, so I'm back to 1. And then when theta is 3 pi over 2, I get 1 minus 4 times negative 1, which is positive 5. So let's just go ahead and graph the 4 values that come from that. So when theta is 0, I'm looking out in this direction here, and my radius is 1. My distance from the origin, 1. All right, when theta is pi over 2, I'm looking out in this direction, but my radius is -3. That means that I look out in this direction, but I march backwards 3 units and wind up here, because I'm going backwards from the pi over 2 direction. When I'm out in the direction of pi, I'm 1 unit out, so I get a point right here. And then when I'm out in the 3 pi over 2 direction, I'm out this way, and I'm out 5 units. And now I have 4 points on my graph. Hard to tell how those are going to be connected right now, because I don't really have any other data to work with. That's why we need to collect a little bit more. So I'm going to try plotting points corresponding to multiples of pi over 4. Some of you tried multiples of pi over 6. Those can work as well. There's no reason that can't work. And in fact, sometimes you get a sine of theta equal to 1/2, which makes this calculation a little bit easier to do. That's kind of nice. But I'm going to use multiples of pi over 4 just because that's the first thing that occurred to me. All right, so this time I get 1 minus 4 times, and I told you that square root of 2 was 1.4, so we're going to use that. Let's see, so what's the deal here? Sine of pi over 4 is root 2 over 2, so that's 1.4 over 2. So that's like 1 minus 4 times 0.7, and that's 1 minus 2.8, which is negative 1.8. Main thing to know is that it's a negative number. So I'm going to get a point out, let's see, so I'm looking in this direction, pi over 4, but I'm going to march back 1.8 units. 1.8, so I'm around here. Okay, now look at that. In just the time it took for me to go from theta equals 0 to theta equals pi over 4, I went from here all the way out to this point. So I'm going to have a continuous curve from this point out to this point. And furthermore, because my radius goes from 1 to negative 1.8, and it's changing continuously, like it's not going to just all of a sudden jump from being positive to being negative, it's going to have to go through 0 at some point. So not only am I going to go from this point to this point, but I'm going to cross through the origin while doing it, because at some point the radius has to be 0. So I'm going to get a curve that looks kind of like this. All right, that's kind of a rough picture, but should be a good way to get started anyway. Okay. Anyway, what about when theta is 3 pi over 4? Then I get 1 minus 4 times, and then again, sine of 3 pi over 4 is about 0.7. So I get 1 minus 2.8, which is negative 1.8. So I get, let's see, if I look out in this direction, 3 pi over 4, I'm going to go 1.8 in the negative direction there as well. So I get a point somewhere out here. Okay, now remember, between those 2 points, I had this point, pi over 2, and a radius of negative 3. So at some point, I'm going to have to connect those 2 points together, this point with this point. So I'm going to connect those with a nice smooth curve, and then go through this point. And then after that, I wind up back at pi, and I'm back to having a positive radius. Now, to get back to a positive radius, I have to go through the origin because my radius has to be 0 somewhere. But then I'm here. Okay, now this is where things get a little bit prettier. All right, when theta is 5 pi over 4, my sine is negative 0.7. So I get 1 minus 4 times negative 0.7. 1 plus 2.8, which is 3.8. So I go out 3.8 units along the direction 5 pi over 4. And I end up, let's see, this is 1, 2, 3, and then 0.8, something like that. So I'm going to go from this point through this point, and then out to this point at 3 pi over 2. And then I will have one more point. 7 pi over 4 gives me a R of 3.8 as well. So I'm going to have a point here as well, I think. Let's see, is that? Yeah, that's the one. And then that's going to bring me back to the, not the origin, but back to the point corresponding to theta equals 0. So I should get a graph that looks kind of like that. I don't know, like looks like a peach with a pit in the middle of it or something. Actually, that has a name. It's called a limaçon. See, with a little beard under it. That's called a cedilla, that little diacritic there. That's called a limaçon, and it is a limaçon with an inner loop. And I was looking for whether that inner loop was there, whether you realized that that radius was going to go negative and then create this little shape inside of the outer curve. Okay, but yeah, one of the main subtleties to look out for is if the radius goes from being positive to negative, in this kind of graph, in a polar graph, there's only one way that can happen, and that is that the radius has to go through 0 at some point, assuming that this is changing continuously, which it is. And if your radius is ever 0, that means you have a point at the origin. You can take that to the bank. Alright, so anyway, that's how you create a graph, is just you sort of doggedly create a table of values and try and get yourself enough data to figure out how the graph is connected. There are other ways of doing it, but they take more practice, which means graphing some more polar functions and sort of comparing results. Okay, anyway, that's it for that question.